Hi everyone, I'm Allan O'Driscoll and I'm a developer for Greenpace. I've been tasked with creating a new security policy that will be used by our development team. I'll be presenting the policy today and I'm looking forward to your feedback. So let's get started. A good security policy uses a strategy that includes defense in depth. This strategy employs multiple layers of protection to enhance the overall security of the system. At the outermost layer, we have the physical security of the environment. This includes things like locks and doors. As we move inward, we see layers that secure the cloud, network, and the host machines. These layers include things like firewalls, access controls, patching policies, and endpoint security. The innermost layer protects the application itself and the associated data. In this layer, we use secure coding practices to protect against known exploits and to guard against future vulnerabilities. The policy outlined in this presentation includes guiding principles, a set of security-related coding standards, and policies regarding automation, encryption, and the usage of the AAA framework. The overarching goal is to provide defense in depth as visualized in the diagram. We'll discuss each of these topics in the upcoming slides. Security is an integral part of the development process. It's one of those jobs that is never truly done. Each coding standard that we've developed can be categorized in a matrix by priority and likelihood of occurrence. When security violations are discovered, we can use this matrix to help us decide which problems we should focus on. The issues with the highest impact and that are most likely to occur should be addressed first. These are shown in red. But we shouldn't stop there. We should strive to fix all the issues. This is a continuous process. New security violations can be introduced anytime the code changes. In addition, new vulnerabilities will be discovered by the development community on a regular basis, and these need to be accounted for in the threats matrix. I'll mention a few specific examples. One of the issues is standard number 3. This is something that, in my opinion, has a high impact and is likely to occur. Specifically, our standard requires that buffers created to store strings are properly sized. If they are not, the program may crash, or worse, it could overwrite memory, allowing the execution of arbitrary code. This type of issue, which is shown in red on the matrix, should be fixed first. Standard number 2, shown in yellow, is an issue that is still likely to occur, but it has a medium impact. Specifically, our standard states that we need to ensure data integrity when converting between types. For example, when converting between floating point types and integer types. If done incorrectly, this can lead to data loss. The issues in yellow would be the second in line to fix. Standard 8, shown in green, is a problem with a low priority, but it's still something that is likely to occur. This type of issue is related to poor data encapsulation and the possible lack of data validation. It's something that is covered by principle number 1, shown on the next slide. This issue needs to be fixed, but it can be prioritized lower than many of the other problems. We've adopted a set of automated tools that can help categorize these issues automatically. I'll discuss this later in the presentation. We've defined 10 principles that form the foundation of our security policy. Principles include validating input data, heeding compiler warnings, architecting and designing for security, keeping things simple, denying access by default, adhering to principles of least privilege, sanitizing data sent to other systems, practicing defense in depth, making use of effective quality assurance techniques, and adopting a secure coding standard such as the one being presented. These principles can be applied to one or more of the coding standards. For example, Standard 6 is related to assertions. Assertions are useful constructs that can help us validate the code during development. However, our standard dictates that assertions should not have any side effects. In other words, if they were completely removed, such as in release builds, the code should function exactly the same. The compiler and static code analysis tools will warn us when this type of issue is detected, so we should heed compiler warnings. That's principle number 2. and we should correct any problems like this when they are detected. Another example is Standard 4, which requires the use of prepared statements when constructing SQL queries with variables. Data must be sanitized before it is sent to the database. Otherwise, the code could be vulnerable to a SQL injection attack. In this case, principle number 7 applies. A third example is Standard 1, which talks about the appropriate use of data types for information stored by the system. An example would be an integer data type that is not large enough to hold all the possible values. This can lead to unexpected behavior in the application. Issues like this can be detected by static code analysis tools and by the effective use of quality assurance techniques, like unit testing. This is something that is covered by principle number 9. The items listed on this slide are the 10 standards that will serve as a starting point for our coding policy. We can add more in the future as our system evolves. The standards have been color-coded using the same colors as the threat matrix. They have been categorized based on the potential impact and the likelihood of occurrence. The issues with the highest impact that are most likely to occur are listed in red. For example, standard number 5 discusses the possibility of memory leaks when memory is allocated but not freed. This can lead to system stability issues and in some cases could be exploited to create a denial of service attack. Issues like this should be addressed as quickly as possible. Next, we have the issues in yellow, which have a medium impact but are likely to occur, or have a high impact but are unlikely to occur. For example, Standard 10 discusses the issue of closing file handles when the related processing is complete. If we forget to close a file handle, it can also lead to system stability issues. But in my opinion, this type of issue is less likely to occur than some of the other problems. Standard 7 requires that all exceptions be handled in the code. It's a bad practice to throw an exception without a plan to handle it. At the very minimum, the code should log a useful error message that can aid in troubleshooting. But it would be even better to take measures to prevent the exception or to at least actively handle it. That's part of a good defense in depth practice, which is principle number 8. Last, standard 9 indicates that we should never hard-code passwords or API credentials. Doing so can expose this information to bad actors. It also makes it more difficult to implement other security practices like password rotation. The application should be architected and designed for security. That's principle number 3. In this case, it would mean externalizing the password and making use of encryption. In the end, all of these issues need to be fixed, but we need to prioritize the work so that the most critical issues are addressed first. Encryption is a critical part of our security posture. We're constantly facing security threats from outsiders, and unfortunately, sometimes insiders. We can reduce our risk and exposure by implementing an encryption to protect our data. There are several scenarios where data needs to be encrypted. The first, and probably most obvious, is data that is at rest. This is data stored on the disk or in a database somewhere. We don't have to encrypt everything, but there are some things that should never be stored in plain text. For example, consider passwords and API keys. In many cases, a one-way hash should be used to protect these critical values. In every other case, they should be encrypted. In general, file systems and databases should also be encrypted using storage level mechanisms, but extra steps must be taken to secure sensitive bits of information when they are at rest. The next category is data in transit. Our policy requires that all data transmitted over the internet or within the local network is secured using TLS and strong SSL certificates. This prevents someone from capturing data on the network and making use of it. In addition, any files containing data must be encrypted when sent over email or any other messaging application. The last category is data in use. This one is a little less obvious, but it applies to some data that is sensitive and needs to remain encrypted while in memory. This helps prevent the data from being discovered if the system is ever compromised. For example, our standard requires that passwords stored in memory are either hashed or encrypted until they are actually needed. At this point, they can be decrypted for use, but then immediately purged. All of this helps to strengthen our security and provides additional layers of defense, which is principle number 8. The AAA framework is another critical part of our security policy. It's a mechanism that allows us to control who has access to our systems, what they can do, and to create a record of their activities. The framework includes three parts. First, authentication is the process of identifying who you are. This is generally accomplished using a username and password. We also require the use of multi-factor authentication for all users. Authorization allows us to specify what each user can do within the application. It is implemented using a system of role-based access controls. Each user is assigned one or more roles, which are checked on every request. The system must check for the required permissions before returning data to the user. This should happen on every request, every API call, and every database query. The last item in the framework is accounting. The system needs to keep a detailed log of what users do. Every login attempt needs to be recorded. This is true whether it's successful or not. In addition, all other important activities need to be recorded. This helps secure the system and provides a mechanism to audit activity and troubleshoot problems. Our security policy requires the use of unit testing. In general, we should strive to achieve 100% coverage. Unit testing allows us to automate test cases within the build process. It also helps to enforce compliance because the build will fail if any test fails. This means that test failures must be fixed promptly before the development process can continue. Positive test cases confirm that the code works as expected in the normal scenarios. Negative test cases confirm that the code fails as expected in exceptional situations. The following slides will provide several examples of unit tests using the Google Test Framework. This test verifies that we can add a single item to an empty vector. It first verifies that the collection is empty. It verifies that the size is 0. It adds a single entry, and then it asserts that the collection is no longer empty and that the new size is 1, and the test passes. To improve this test, we could verify the actual value that was inserted. We could also try to add more than one item. This test verifies that the vector's capacity is always greater than or equal to the size. It does this by first confirming that the collection is empty. It checks that the size is 0 and that the capacity is greater than or equal to the size. It then adds a single entry to the vector. It verifies that the new size is 1 and that the new capacity is still greater than or equal to the size. And then it repeats this test with an additional 4 items and then an additional 5 items after that. And in each case, verifies the expected size and that the capacity is greater than or equal to the size. And the test passes. To improve the test, we could create another test that does the same thing but in reverse order by deleting items from the vector. This test verifies that if we resize a vector to a smaller size, that the vector size will decrease and possibly truncate items from the list. The test first sizes the list to 10 items, then verifies that the collection is actually sized at 10. Then it gets the current size, calculates a new size, which is 5 less than the current size. It resizes the collection, and then it verifies that the collection is now at the new size and that it's not equal to the original size, or rather than it's less than the original size. And the test passes. To improve the test, we could try to resize to a negative value, or we could try resizing to the same size, which in theory would result in no change. This test verifies that we can insert items at the beginning of the vector. We start by asserting that the vector is empty. We then push the value 1 to the beginning of the vector. We add 20 more entries. Then we verify that the first item in the vector is actually a 1. We then insert a 0 at the beginning of the vector, and then we test that the new item at the front of the vector is now 0 and that the next item is 1 as it should be, and the test passed. To improve this test, we could also try inserting items at the end or even in the middle of the list. This test verifies that we get an index out of range error when we attempt to access an item with an index that is beyond the end of the list. It does this by first resizing the collection to 10 items. It then verifies the new size of the collection. It then attempts to access the 11th item, which is out of range, and it should throw an out of range error. And this is a negative test that proves that case, and the test passes. To improve this test, we could start by ensuring that we can successfully access the last item in the list before we attempt to access beyond the end. This test attempts to reserve one more than the collection's maximum size. This is a negative test that should throw a length error, and it does exactly that, and the test passes. To improve the test, we could attempt to reserve one less than the max size, but this would likely still throw an error because the system most likely wouldn't have enough memory to complete the request. This diagram shows Greenpace's existing and well-established DevSecOps process. The process can be visualized as a continuous loop. Whenever one cycle completes, the next one begins. In explaining the diagram, we have to start somewhere, so let's begin with the assess and plan phase. We need to be aware of any new threats that may have an impact on our application. We need to fill the backlog with this new information and prioritize any new tasks. Next, in the design phase, we need to determine how these changes will be implemented. We also need to determine how we will test for any new vulnerabilities. The build phase is where our automation kicks in. We will integrate our unit tests and include automation for dependency checks and static code analysis. Unfortunately, we have not identified a single tool that covers all of our requirements, so we'll integrate multiple tools, including Google Unit Test Framework, CPP Check, SemGrep, and Clang Tidy. Any critical or high issues found by these tools will cause the build to fail and must be fixed with priority. Other issues will be analyzed and added to the backlog. In the next phase, we continue our QA. We have additional scans for build artifacts and additional security testing. For example, the development team will use the OWASP Z attack proxy tool to perform security testing. Any critical or high issues reported by this tool must be addressed immediately. Our policy also requires that we contract with a third-party firm to conduct professional penetration testing. This will be scheduled on a yearly basis. From here, we cross into production. We use Terraform-based automation to handle all of our deployments. Part of this will include deploying auto-scaling groups and load balancers so that the system is highly available and fault-tolerant. The application and automation will be designed to support health checks and a self-healing mechanism. Unhealthy instances will be terminated by the infrastructure, and new instances will be launched to replace them. The policy also requires the installation of security tools for continuous monitoring. These include CrowdStrike and Rapid7. The installation and configuration of these tools will be handled by the automation. This takes us to the monitor and detect phase. All log files and system metrics will be collected by an OpenObserve system that gives the operations team visibility into what is happening. CrowdStrike and Rapid7 tools will actively scan each system and report findings to the security team. The policy also requires the use of a web application firewall that is capable of automatically detecting and blocking suspicious requests. Alerts will be configured for unusual activity and known error conditions. In the response phase, the operation team is proactive about monitoring the system and responding to alerts. Any production issues that have impact on customers require a root cause analysis to understand what happened and how it can be prevented in the future. After responding to any issues, the operation team takes steps to update their runbooks and return the system to a stable state. And then the cycle repeats. This slide shows the phases in the DevSecOps process that include the use of automated tools. These were mentioned on the previous slide and will be summarized here. In the build phase, our policy requires the use of the Google unit test framework with a desired test coverage that approaches 100%. We also use CPP check, semgrep, and clang tidy as static code analysis solutions. In the verify and test phase, developers will conduct security testing using the OWASP-Z attack proxy. Issues found by this tool will be fixed with priority. In the transition and health check phases, the operations team will use Terraform for automated deployments. They will make use of load balancers and autoscaling group to provide high availability, and they will also install and configure CrowdStrike and Rapid7 for continuous system monitoring. The monitor and detect phase will include the use of a web application firewall that will automatically detect and block suspicious activity. An open observe system will be used to collect and aggregate all logs and metrics. CrowdStrike and Rapid7 tools will report findings directly to the security team. Additional tools may be introduced in these and other phases in future iterations of this policy. Security is a major industry these days. There are a lot of people that will attempt to take advantage of weaknesses in the system. Some of them have no objections to breaking the law to gain advantage for themselves. Though, we have a big problem, and we need to take steps to protect our application from these bad actors. We must protect the integrity of our systems and the associated data. Our customers expect us to do this. If we fail, there are consequences. The stakes are high. We could face legal headaches, be forced to pay penalties, suffer damage to our reputation, and take a hit on our bottom line. If we act now, we have a good chance of reducing the overall risk by staying ahead of these bad actors. However, if we delay, then we are passively choosing to accept the risk and the associated consequences. There is a cost to security no matter what you decide to do. However, I believe that the cost is much less if we stay on top of the security issues rather than paying the penalty after an attack. The main recommendation from this presentation is to simply adopt this security policy. It's not perfect, but it's a start. Security must be a priority for everyone. We will not succeed unless we have support from all levels within this company. The largest gap in this policy is related to the coding standards. This policy just scratches the surface of what should be included. We need to add additional standards to provide full coverage to the overarching principles. This should be a team effort, and this will be a living document that constantly evolves. It's necessary because the security landscape is constantly changing. Every day, new vulnerabilities are being discovered. Our development processes are constantly changing as well. Today we use C++, but tomorrow we may start using Java or Python. When that happens, the security policy will need to adapt to cover the new tools and technologies. Speaking of tools, new security tools will also be developed, and existing tools will be enhanced. We will need to research and adopt these tools as they become available. We have a good starting point, but we will need to continue this effort to improve our processes by implementing best practices in every step of the development process. As mentioned earlier, this document is just a starting point. There are several other standards that should be reviewed and adopted to prevent future problems. The first is the SEI CERT C++ coding standard. Much of this document cites existing standards from this source. It contains a comprehensive list of coding standards for C++ and a number of different languages. The OWASP Application Security Verification Standard is another good resource that includes a comprehensive list of topics that should be covered during security testing. The CIS benchmarks are a third resource that provides audit and remediation procedures for Hundreds of topics covering all the major operating systems and applications like web servers, databases, and containerization solutions. It's a paid resource, but it's well worth the money. The last standard is the AAA framework. This includes authentication, authorization, and accounting, which are all necessary features for a properly secured application. Speaking of AAA, I wanted to mention one recent example, which is the 2024 Snowflake data breach. Snowflake is a company that provides data warehousing capabilities as a service. A few of their largest customers include AT&T and Ticketmaster. Both were impacted by the breach. In AT&T's case, call log and messaging data for over 100 million users was stolen. In Ticketmaster's case, information for over 500 million customers was taken. This was made possible partly because of poor management of user account information and the fact that they did not require MFA. This issue still hasn't been fully resolved, but just a few days ago, AT&T announced that they agreed to pay a $177 million settlement for the incident. This was a very costly breach, and there were hundreds of other customers that were impacted. We need to be security-minded in everything that we do. Sometimes we're tempted to just jump into things and start building features, but that's the wrong way to start. We need to think about security before writing the first line of code. Security should be by design and never as an afterthought. Don't leave security to the end. This policy will help make sure that that doesn't happen.